That will give an idea of what the exam will be like from previous offerings. So this term is every term is going to be slightly different, but the overall structure and the overall question structure and the mark distribution should be similar. And by all means, look at those. Those will be very helpful for you to prepare for your exam. And if you have any questions, please let us know, and we'll help you with those past exam questions as well. Let me see. Okay. Other than that, let's continue our discussion in relational algebra and query execution. So in the first half of, because it's been a while, so we're going to have like a recap of what we've discussed. So in the first half of the course, we talked about how to use SQL, and how to connect SQL to Python. And basically, we talked about data manipulation language, data definition language, and all sorts of things. But SQL inherently is a declarative language. So it's kind of neat that we just have to write what we want from the database. And if you think about it, it's kind of like a natural language way of interacting with the computer. So SQL is declarative. You say what you want, and then you're getting it. But in the second half of the course, we're kind of digging into what is really happening in SQL engine. So we want to know what is happening when you're writing the SQL query into PostgreSQL. What's happening is that they're parsing your query into a bunch of relational algebra expressions, and then it will try to look at a lot of equivalent relational algebra expressions. So basically, SQL is kind of, so basically it can translate SQL into a relational algebra expression, and then each relational algebra expression represents a query execution plan. So in the later part of today's lecture, we'll see that we can break down one RA expression into a bunch of steps, and then that will be just one query execution plan. And what the SQL engine is doing is that it will look at many equivalent relational algebra expressions, each representing a execution plan, and then it will estimate the cost associated with it. So the good thing about the optimizer is that the optimizer does not always look for the best execution plan, because if you have like a lot of tables and if you have very complicated query, the number of the search scope for all possible execution plan is like huge. So what it does is that it will kind of grab a subset, and then it will get the approximately the best. So if you learned like algorithm theory and stuff like that, you know that to get something exact, to get the exact solution, a lot of times is NP hard and is NP complete. And a lot of times in reality, from the engineering side, we can just settle with an approximately the best one. So that's what the SQL optimizer is trying to do. It will probably spend like 50% of the time grabbing meaningful execution plans, and then spend probably 50% of the time computing the estimated cost, and then it will find the best out of those, not like from all possible execution plan. So it strikes a balance between trying to find all of them and versus, but it still produces a pretty good result. And that is the reason why we want to learn relational algebra. Relational algebra is basically the mathematical representation of our SQL queries. So I think we have briefly talked about the most important ones, especially those on the single relation. We talked about selection, production, and we kind of talked about the set-related operators like union, intersection, and differences. And today we're going to talk more about product and join, and in the end we're going to talk about division. So to have a recap, so selection and the projection are basically trying to grab data from the relation from two different angles. So projection is basically selecting the columns, and selection in relational algebra is selecting the rows, so filtering the rows. So that's the difference. And one huge fundamental difference between relational algebra and the SQL is that relational algebra operates on sets, while SQL operates on bags or multisets. So the reason why there's a difference is because relational algebra is trying to get a mathematical representation of your query. So mathematically, we need to define them as sets. So by default, every relational algebra expression, it will be a set. So no duplicates allowed in the set. But in SQL, this is a real implementation. It's based on multiset or bag, which means that a table can have duplicate rows, as you have seen. And the reason why SQL does not automatically remove duplicate rows is because it is expensive. So sometimes you can just settle with not unique rows, and you can just be happy with that. And we'll talk more about why removing duplicates is very expensive once we get to the multi-version concurrency control part of the course. So basically, the gist is that relational algebra operates on sets, and the SQL language operates on multisets. So anything returned from relational algebra is going to be deduplicated. Okay, and also we talked about the rename operator, and let's just review a couple of examples. So first, we want to rename the columns in the beers relation. So beers used to have the columns beer and brewer, and now what we want to do is that we want to rename them as beer and, so we want to rename the name and brewer as beer and the manufacturers. So basically in SQL, you can easily do that using the as operator. And in relational algebra, you can basically put the input relation into the brackets, and then you can basically dictate the names of the columns in the subscript of the rename operator. And usually, if you go to a textbook, if you see other YouTube videos about relational algebra, you see that they use Greek letters. So we're not going to use Greek letters in this course. We're just going to be happy with English. So basically, in a textbook, in a YouTube video, like selection is theta, sigma, and then projection is rho, and then you have the gamma operator, things like that. And then a join is basically a bow tie. And we don't require to memorize any of that, so we just use plain English. So basically, if you want to rename the beers table into beer and brewer, if you want to rename drinkers table into name, suburb, phone, that's how you do it. And the reason why do we need a rename operator anyways? Like it sounds like it's not really, does not seem like very useful compared to selection and projection. And one of the usage case is when you want to do a self-join. So let's just say that you have, for instance, you have a bunch of people, like a bunch of students from different states in America or from different cities in Australia, and then you want to get like all pairs of the students within each city or within each state. In that case, more often than not, you need to perform a self-join. And when you're performing the self-join, the relation names are the same. So a very direct use case of rename is that basically when we're doing a self-join, what we could do is that we could rename them into a different table, and then we can join these tables under different names as if they're different tables. So because if you're joining drinkers with drinkers, and then you need to put the join conditions over there, and then they all have the same attributes, and it is very confusing whose name is that and whose address is that. Like it's not really clear where's that attribute coming from. So to get around this, we can rename them into different tables, and then we can just perform a join on D1 and D2. So this is a breakdown of the. So this is like a step-by-step relational algebra breakdown, and that's basically the SQL code. And in SQL code, this is easy. We can just call drinkers as D1, and then it's joined with another drinker D2, and then we can just say D1's address needs to match D2's address, and also the name should be different. And that way we can get all pairs of the people from the same address or from the same city in a different database. So renaming can be useful in this case. And projection is kind of like select distinct in SQL. So basically you're projecting your table or your relation into some specific columns or attributes. So let's walk through this. I think we have talked about this before. And so if you want to get the names, we can just project beers into name, and then in the end, it will get all distinct names of the beers. And the manufacturer works the same. And here, this is a slightly more complex relational algebra. We're looking for all of the drinkers who live in Newtown. And in this case, first we do a filtering. First, we filter all of the drinkers in Newtown, and then we project the name. And note that, I think I mentioned this before, sometimes it seems like these operators can be associative, which means that you can change the order. But a lot of times you need to really be careful when you try to switch the order of these operators, because you need to be mindful of what does the schema look like after each operator. So like in drinkers, if we just do a selection, we're just filtering on the column address. It doesn't really change the schema, right? So after that, we can go ahead and do whatever projection we want. We can grab whatever column we want. So this is safe. This is very safe. But if you just flip it, and if you project to name first, and then you select based on address, and then there's a problem, because after you project it into a column or a couple of columns, the schema changes. And then maybe after you change the schema, you can no longer use address to filter the rows. So be mindful. So a lot of times, especially when we have a giant table, sometimes you can get away with switching the operators without changing the end result. But that's, from my experience, that's like the one huge source of mistakes. Okay, selection. Selection is basically, we have seen before, we're filtering the rows. So selection in SQL, usually it translates to a where clause. So we're selecting different columns in SQL, and then in the end we say, hey, we want all of the places, we want all of the students from New South Wales. So we get a filtering condition in the end. So selection usually translates to where or having in SQL code. So these are the 3 pieces of SQL code corresponding to these 3 questions. So we have already seen this before. First, we want to get all of the bars from the rocks, and we want to get all of the beers made by a specific brewer, and also we want to get all of the beers sold in a specific bar. So these are pretty easy, since you have already done Simon 1, Simon 2, and these are the equivalent relational algebra. So basically, when you type this into PostgreSQL, it will parse that, and then the optimizer will actually look at something like this. And then it will look at this expression, and then it will try to tweak it into different execution plans, and then it will kind of pick the approximately the best one. So this is not, so for the first one, we are filtering on the address column, and then for the second one, filtering on manufacturer. And in the last one, again, we're first filtering on an attribute, and then we'll project into the other attribute. So usually we want to apply filtering as fast as possible, because that can reduce the size of the intermediate result, and that will speed up the query process. So what usually happens is that even if you write it as you project first and then you select later, SQL optimizer will recognize that, and then when it is producing the approximately best query execution plan, it will flip them around, and then it will apply filtering as soon as possible. So we'll talk about how this can affect query efficiency in the next hour. So projection, so these operators are based on single relations. So projection, grabbing the columns, selection, grabbing the rows, as well as what else we got? Renaming, changing the names. And but if you want to model queries across different relations, we need two strategies. So vertically, we can use set operations. So basically, this is where we talked about union, intersection, and differences. And also, we can do horizontally. We can horizontally expand the table. So this is where we talk about Cartesian product, join, natural join, theta join. So I think we mentioned the definition of the set operators. So the most important thing you need to remember, the same thing in SQL, is that if you want to do union, intersection, or difference, you need to make sure that those tables are union compatible. So basically, union compatible is just a fancier way of saying they have the same schema. So two tables need to have the same attributes, the same order, to be able to, so that we can do union, intersection, and differences on them. So that's union compatible. I'm not sure why they said it's union compatible. Why don't they name it as intersection compatible? I mean, it's the same thing, basically identical schema. And we'll talk about product and joins later. Let's look at some examples in union, intersection. So so before, this is a different person, but I couldn't pronounce that person, so I changed to Alice. So two classic examples we looked at in SQL. Want to find bars where either of those two people drinks, or want to find bars where both of them drinks. And we can also find the bars where John drinks and Alice don't drink, and the other way around. So in SQL, this is the SQL implementation of those two. So first, we filter all of the bars where John drinks, and then we find the bars where Alice drinks, and then that will be two set of bars, and then we take the union. And the second one, we're basically taking the intersection of those two sets. And this is the relational algebra equivalent. Let's look at. So basically, in relational algebra, this acts as a query execution plan, and the query optimizer will look at these steps and then consider this as a plan, and then it will compute the cost associated with it. So this looks like pretty much nothing we can really optimize from. So we grab all of the bars where John drinks, and then we grab all of the bars corresponding to Alice, and then we take the union and we take the intersection. And very interesting question a lot of people wonder is intersection really needed? Like we already have, if we have like union and differences, is the intersection operator really improving our expressive power in relational algebra? So this is more like a discrete math problem. So if we had a union operator and we have a difference operator, does the intersection operator improve or add to our expressive power for relational algebra? So basically, I'm asking, how can we, is it possible we can express intersection in terms of union and difference? So can we do that? Like, if you take discrete math, this should be, we can do that, right? Yeah, how do we do it? How do we do it? Union minus difference? Like say I want to get, the intersection between A and B, and I only got like union and difference. Yeah, so basically, basically you can express it in other operators. So we can use, let's say we want to get the intersection between E1 and E2, and then if you can just get E1 minus D2, and then you can just use E1 to get rid of the difference, then that part is the intersection. So could have made more sense if you had a Venn diagram here, but so basically E1 intersect E2 is their common part, and then E1 minus E2 is the part that are the tuples in E1 but not in E2, and then if we get rid of those tuples in E1, that will leave us with the common part. So so the whole point of this is that intersection is not really expanding our expressive power in relational algebra, but we choose to let it stay so that relational algebra can be simpler. So basically, basically we're saying that if we had a union and difference, intersection is a byproduct, and this kind of thinking extends to other operators as well, as you can see later. So this is a slightly more complex example, and we're going to briefly walk through it and really look at how relational algebra can represent a query execution plan. So and the question is, we want to find the drinkers who frequent bars in either this town, in either Newtown or the Rocks, and also likes the beers made by Carlton. So this is kind of like a two-step problem. First, we need to find the bars in those suburbs, and then we need to find the drinkers who frequent these bars, and then we need to find the drinkers who like Carlton beers, and in the end, we need to take the intersection of the two. So and note that here this is the intersection sign from discrete math, but if we ever ask you to write anything say in an exam or something, you can just write the plain English intersect. So because we don't want to bother with Greek letters, so whenever we want to ask you to give us relational algebra expressions, you can just say union, you can just say intersect, and you can just say projection. So you don't need to use those Greek letters. Okay, and let's look at this exercise where we visualize the result size associated with the following relational algebra. So this is important because when we are writing relational algebra step by step, we need to really think about what is the result size of that expression. And that is actually how the query optimizer is looking at your relational algebra. It will look at your relational algebra to break it down, and then for each step, it will kind of estimate how large that table is. And if it's too big, then it has memory issues. If they can switch things around to make it smaller, that'd be better. So estimating the result size is very useful from the perspective of SQL engine. So let's just pretend we're the SQL engine, and let's kind of guess the result size of the following relational algebra expressions. So we're looking at a relation. This is an imaginary relation A, B, C. So it has three attributes, 3 columns, and it has 1,000 tuples, basically 1,000 rows. And we're going to estimate the size of the following relational algebras. So the first one is we want to estimate the size of this expression. So basically R is renamed to T, and then the columns are renamed to JKL. So let's just go back to the previous slides so that we cannot see the solution. What if we just do a rename? Like, what is the size of that? This should be like a no-brainer. 1,000, right? Because we didn't do anything. We literally didn't do anything but renaming the attributes. So if R is 1,000 tuples, then renaming it will be 1,000 tuples. What if we project R into 2 attributes, A and B, and let's just assume that currently we don't know anything else about these attributes. We don't know if they're primary keys. We don't know they're unique or whatever. And we're looking at a relational algebra here. So what is the estimated size if we project it onto A and B? So you can give me a range, like any range. So what happens if you really project it into, like originally it has 1,000 rows. If you project that into 2 columns, what happens to the strength? What happens to the length? Is it going to go larger or going to be lower? Or is it going to stay the same? Pardon? Same. Why? Pardon? Oh, I think that's very good thinking. So if one of them is a primary key, then we can safely assume that the result size is exactly the same as before. But right now we're not making additional assumptions. Like we don't know which one is the right. Right now we don't know which one is the primary key. So like it could be C is the primary key, could be B is the primary key, could be A, but we don't know anything about the relation yet. So usually what happens with projection is that in SQL, if you just select a bunch of columns, because it does not remove duplicates, it will give you the same length as the original table. In relational algebra, because you removed one attribute and you're projecting it onto A and B, so basically, whenever you project into a subset of the attributes, the result size will shrink because it will automatically remove the duplicate tuples from it. And the same happens when you project into B and C, because originally it is a table, which means that the combination of A, B, C in the table should be unique. But if you get rid of some attributes, like if you get rid of the attribute A, then the combination of B and C may not be unique anymore. So for instance, we have like 1, 2, 1, 2, 2, 1, and then this is a legitimate table. If you get rid of the first column, the table becomes 2, 1, and 2, 1. And then in relational algebra, because this is based on sets, it will remove the duplicate for you, and then you're left with 2 and 1. So 2 and 1 is smaller than the original size. And so basically, when we're renaming it, this doesn't change the size. When we are projecting it, the size can shrink or it could be the same. So the size is basically less than or equal to 1,000. And what about selection? So selection, we're selecting the tuples where A is equal to a specific value, and we're selecting, so all these relational algebra expressions we're selecting the rows where A is not a specific value, and we're selecting where A is exceeding a specific value. So what is the size of the result? So there's something called selectivity. So selectivity is basically the fraction of the tuples satisfying the condition. So if you're doing a filtering, so let's just say that, so all these 4 operations, they're kind of the same. Basically, they're applying the selection operator to the schema, and then in each of the relational algebra, we have a condition. And then if we just say S is the selectivity, which is the fraction of the tuples satisfying these conditions, then the result size should be just 1,000 times S, right? So 1,000, originally we have 1,000 of them, and then only S proportion of the whole thing satisfy these conditions, then the result size will just be 1,000 times S. So that's how, for instance, if S is like the fraction of tuples satisfying A equals C, then the selectivity of A not equals to C will just be 1 minus S. And in that case, the result size of the first expression will be 1,000 times S, and then the second will be 1,000 times 1 minus S. So it's unlikely you ever need to actually do this kind of calculations. And the point of this exercise is that to ask you to stand in the shoes of the query optimizer. And this is what the query optimizer is doing every day. So you give it a bunch of SQL statements, and then it converts to relational algebra. And then it needs to rely on what information it knows to estimate the size of your result. So if you're just renaming it, the SQL engine knows that you didn't do anything, you just renamed it. And if you're projecting it, the SQL engine knows that the result of this is at most 1,000. And then if you're just doing selections, like that, the SQL engine, it can compute the selectivity based on the distribution of your data, and then it can estimate the size of these relational algebra expressions for you. So that's how relational algebra. That's how relational algebra is used in the SQL engine. And then let's look at products. So these exercises, they're related to selection, projection, and renaming. So they're not at this point is not as complex because we haven't even talked about product and joins yet. So product is basically the Cartesian product, and in this case, we're trying to expand the table horizontally, and everything can be expressed as a product. So product is the most important operator when it comes to horizontally expanding the relation. So basically, mathematically, this is the Cartesian product of two relations, and the schema is basically the union of those two, the original two schemas, and then in each row, we're taking the combination of those two tables. So basically, we have like two relations R and S, and for each combination of them, we make a new tuple, the concatenation of the two, and then we put that as the result of the product. And for product, the result is fairly large. So basically, the size of the product is basically the product of the sides. So that one you can guarantee it because you're basically getting all combinations of the tuples. So if you take Cartesian product, and if you want to know how many tuples in the end, we can basically get the product of those sizes. And so this is the this is a very clear example. So R has A, B, C attribute, S has X and Y attribute, and the Cartesian product of the two, the schema is basically the union of those original tables, and then each row is a combination of R and S. So we take one row from R, we take one row from S, we put them together, and then we put it under the Cartesian product. And the reason why Cartesian product is so important is because it's the building block of all joins. So when you were working with SQL, I think you have already experienced this. If you just write select a bunch of or select everything from two tables, and you don't specify the filtering condition, it will just give you the Cartesian product of the two. So if you have like the first table is 5 rows, the second table is 100 rows, you just select everything from those two tables separated by comma, and you don't say which attributes match which attributes, it will just give you 500 rows, and that's a disaster a lot of times. And the reason why I say joins are basically filter Cartesian product is because if you add the where clause and you just put the joining conditions over there on top of the product, and then it becomes a join. So the two types of joins that are interesting that we are talking about all the time. So we're talking about the theta join and the natural join. So the most important join in relational algebra as well as in SQL is the theta join. So theta join is basically, so when people talk about join, they're really talking about theta join. So the difference between theta join and the natural join is that theta join is more expressive. So theta join is basically, let me go to theta join first. Theta join is basically Cartesian product, and then we apply some row filtering based on a Cartesian product. And for natural join is basically an equijoin based on the attributes that are named the same. So natural join is a subset of theta join. So a natural join is basically where if we have like two schemas and they have some common attributes, and so basically we're assuming that the attributes with the same names are the same attributes across different tables. And then what it does is that it's trying to match the values of those common attributes and grab them. So this is the algorithmic view of natural join. So basically we go through each combination of the tuples, and then we check whether those tuples match in those common attributes, and if so, we just attach it to the result. So you shouldn't be and you should be familiar with this already, because I think we have already done a lot of natural join in SQL. So this is the illustration of natural join. We have A, B, and C, and then S is C and D. If you just do a natural join, what it does is that it will look at the common attribute. Actually, the common attribute is C, and then it will try to match all of the rows where the C column agrees. The C columns agree. So basically, that leaves us with two rows. So X, Y, Z, X, Z ended up with two rows where C values are X and Z. So this is a natural join. A natural join is a special case of equijoin. Basically, equijoin is basically instead of assuming that you're joining on common attribute, in an equijoin, you need to specifically saying which attributes should be agreed, should be the same. So in here, in natural join, we don't really say which attributes we're joining it on. We're basically assuming we're joining on the common attributes, and in an equijoin, we need to say r.c equals S dot C. So an equijoin is a more robust way of doing it. And an equijoin is also a subset of theta join. So theta join, let me look at a theta join. So theta join is basically we're doing the Cartesian product, and then we're selecting rows on top of the Cartesian product. So in the rows, and that C, capital C, is super important here because that C over there represents a bunch of conditionals we need to check for those joins. Like in the case of equijoin, C is basically a bunch of like R dot C1 equals S dot C1, R dot C2 equals S dot C2. And then in the case of natural join, the C here is basically matching all the common attributes and then see if they agree. So theta join is the most expressive one and is the most flexible one. And in theory, if you know how to use a theta join, you're good, you're set. So a theta join works like this. The conditions can be much more flexible, and then you can actually use theta join to express equijoin as well as natural join. So the reason why we still keep natural join is because it's used a lot, and it is sometimes people get lazy and they don't want to write the joining condition, and that's the only reason. So this is the example of theta join. You have a bunch of you have two tables, and they don't necessarily have the same columns, unlike in the natural join. And in here, you just take the Cartesian product of the two, and the first table has 3 rows, and then the second table has 3 rows, and then the Cartesian product should have how many rows? So the Cartesian product of those two tables should have like 9 rows, because the first row is matched to 3 rows, second row matched to 3 rows, and then third row matched to 3 rows. In the end, we have 9 rows. But in those 9 rows, we only keep the ones where C is larger than D. So in here, it is, so here, C and D are basically letters. And basically, we're grabbing the cases where C and D are not the same. So we're getting rid of the cases where C is X and D is also X, and we're only leaving the cases where we're only keeping the cases where they're not the same. And so as you can see, that theta join is much more flexible and expressive than a natural join as well as equijoin. So in theory, if you know how to use theta join, if you know how to implement theta join in SQL, then you're set. So it's actually the most frequently used join in SQL queries. And when people say join, they're talking about theta join. And and here we also need to ask the question, is theta join itself, does theta join adding our ability to express relational algebra? Well, actually it doesn't, because if we have cross product and if we have selection, a theta join is basically applying selection on top of the cross product. And but we still keep theta join because we don't want to always write everything in terms of cross product. So in practice, it is very rare we write a relational algebra from the cross product, because that would be super complicated. And in practice, we still use these common operators like theta join and natural join. So basically, we've talked about selection, union, Cartesian product. And then for the other operators, they're kind of derived. For like intersection, it can be derived from difference. Theta join can be derived from selection and Cartesian product. And natural join is basically a special case of theta join. But we still keep these operators because they're very frequently used. Okay? And let's take a look at the exercise. Let's go back to the shoes of query optimizer. And and really estimate the result size of these relational algebra expressions that are related to joins. So let's just say that R has 1,000 tuples and S has 1,000 tuples, and what else assumption do we make on these relations? Okay, it does not say they're really union compatible, and that's important because if they're union compatible, it means that A, B, C are basically C, D, E. So they have one common attribute C, and that's interesting. And then we need to kind of estimate the result, the size of this relational algebra expression. So R has 1,000 tuples and S has 500 tuples. So what is the size of their product? Yeah, 500,000. Just get the product of the size of the product is basically the product of the size in this case, which is very neat. And then, so that's the easiest one. So what about the joins? So if we let's look at what joins are here. So join R and S, no context. It's basically saying this is a natural join. So join R and S, no context, no extra condition. It's basically saying that you should join in the condition where R.C equals S.C. So we're joining on the common attributes. And the second and the third one, they are the equijoins. So basically, they are specifying the attributes that we need to be equal, that we need them to be equal. So we're saying that A equals C here, and also B equals D here. So these are equijoins. And then the last one is a theta join. It's the most flexible join. And it's basically we need to get the rows where B column is larger than D column. And how do we estimate, think about how do we estimate the size of these joins? You can start by giving me a rough estimate. So let's just say that we want to estimate the size of the natural join. Yeah? 500? That's a good guess. And can you give me a range? Is it going to be 500 exactly? Less than or equal to 500, exactly. So that's a very good guess because when you're joining these things together, you're basically applying the select operator on top of the product, and then like the previous examples we have seen, the size of their end result really depends on the selectivity of these conditionals. So since we don't know how many times, how often are these attributes agree, what we do know is that the size should be between 0 and 500. Because for the natural join, we need to find all of the tuples where the C columns are agreeing with each other, and then the number of unique C values in R and in S is capped as 500 because 500 is less than 1,000. So that's a good guess. And for any type of theta join, the result size could be between 0 and 500,000. Because in theory, you're basically applying the selection operator on top of the Cartesian product, and the Cartesian product has the size of 500,000, and then depending on how many times these conditionals are satisfied, it could be between 0 and 500,000. So I think a better way to represent this result is that we can say the selectivity is S, and then the result size is 500,000 times S. Okay, and okay, let's take a break for 10 minutes, and we'll come back to more practical aspect of relational algebra. Okay, I forgot to mention something. So I think I've seen some students on the forum. So if you have question about your marking from the previous assignment, you should email your marking tutor. So if you email me, I didn't mark your assignment, so I wouldn't know what's going on there. But when you're emailing your marking tutor, feel free to CC me, so I can kind of push them to handle your question. And usually, sometimes it could happen when your submission didn't. It happened a couple of times where students passed the auto tests, but they submitted the wrong version or something like that, and things like that needs attention from the TA. So in that case, you need to email the marking tutor. You can find an email from the Moodle's feedback, and then feel free to CC me in that email so I can make sure that they respond to you, okay? And okay, let's get back to relational algebra. So so basically, we need to understand what are theta joins and what are natural joins. So basically, we need to understand that there are special cases of the Cartesian product. They are basically Cartesian product followed by a select operator. And that will allow us to understand and estimate the result size of these relational algebra expressions. And so this is another example illustrating what is really going on with natural join. So we want to get all of the name and addresses of the drinkers who like beers made by carton. What we could do is that we could get the Cartesian product of all these tables, and then after that we filter based on these conditions. We're saying that the drinker's name should match likes drinker, and beer's name should match the beer in likes table, and we also need to say that the beer's manufacturer is carton. So. But by the way, where are we getting these conditionals from? Where are these conditionals coming from? It should come from the foreign keys, right? So basically, this is kind of like the logic when we are writing the implicit join in SQL. We basically put all of these tables on after from. So if we don't put the where clause after it, it will just return us a joined table, which is the Cartesian product of these. Which is the Cartesian product of these participating tables. And after from, we write the where clause based on the foreign keys so that we can apply these joining conditions afterwards. And then in the end, we project to the columns that we're interested in. And if you write it in natural join, the syntax is much cleaner. Basically, if you write a join or a bow tie symbol without specifying any joining condition, then by default, this is a natural join. It will look at the common attribute between drinkers and likes, and it will also look at the common attribute between that intermediate result and beers, and then it will apply those filtering afterwards. So that helps us to understand natural join. And these are some more examples of how relational algebra expressions are written related to joins. So if you want to answer questions like who drinks in Newtown bars and who drinks beers made by a specific brewer, in those cases we need to link more than one table together using joins. And in those cases we can write them like this. So basically, we can first filter all of the bars in Newtown, and then we can join that table with the frequency table, and then in the end we can get the drinkers. So note that we don't use any of the Greek letters. We just need plain English to represent this relational algebra. So let's look at a couple of more examples of how can we map SQL two relational algebra expressions. So some of these examples we have already seen. So bars where either these people drink, and the difference of the bars of those two people. And I think this is the slightly more interesting one, because this involves join, unlike the other ones. So if we want to find all of the bars selling a specific beer at the same price as CBH charges for the VB beer, then we can tackle this problem in different steps. And in the first step, we can compute the exact price at which the CBH bar is charging for the VB beer. So basically, we can project the sales table into price. So before that, we need to filter. We need to filter by bar, and we need to filter by beer, and that will give us a specific price. And then we need to find all of the beers sold in. We need to find all of the rows corresponding to beer new. And in the end, we need to join this table by specifying that the selling price is matching the price that we computed before. So in the first step, we have computed the CBH charges how much money for VB. And then in the joining price, we need to use that as part of the theta join so that we can recover the bars that are selling new at the same price as CBH charges VB. So let's look at another example. So we need to find the beers sold at the same price as. So that's not very different. So sometimes we need to answer the question like which beers are sold at all bars, which rows in the first table corresponds to every row in the second table. In that case, we need to introduce the division operator. So first, we need to project sales into beers and bars, and then in the denominator, we need to get all of the bars from the sales table. And in the end, we can make the division, and then the result will give us all of the beers that corresponds to all bars. And the important part about the division operator is that you need to make sure that the denominator is a subset of the numerator. So basically, you cannot divide. Whenever you want to divide two relations, you need to make sure that the attribute here is a subset of the attribute here. So otherwise, the division does not hold. So this is classically handling the for all queries. If you want to find out all of the tuples in the first table that corresponds to all tuples in the second table, then you need to divide the first table by the second table. So so as we have seen that we can answer questions like which beers are sold in all bars, and in SQL we don't really have a direct. At least in PostgreSQL, we didn't really have the direct divide operator. So if you can remember what we did in the practice exercises, we needed to use something like not exists to get around it. So basically, the division operator can also be expressed by the other operators, other basic operators. So even if we don't have that within a database system, we can always get around it and use the basic operators to express the division operator. Just like before, we didn't have, in the practical exercises, we didn't really have the division operator, but we were able to get the beers sold in all bars via not exist syntax. And also another way we can get it is, I think we provided two solutions. The other way we can do it is that we can use group by and aggregates, and then we can find the number of bars corresponding to the beers, and then we can filter by the maximum number of bars to get the beers sold in all bars. Okay, so that wraps up, so that completes all of the basics of relational algebra. And now we're going to talk more about how it's related to DBMS architecture. So COMP3311 is not a course on DBMS architecture and is basically teaching us how to take advantage of the PostgreSQL database. And if you really want to know what is happening under the hood, how to implement these relational algebra operators, how these data are stored in disk, you should take the course COMP3311, and that's a very interesting course offered by CSE as well. So after you take 3311, it's kind of recommended you take 9315 because it allows you to understand more about the database. So if you're a database, if you become a data scientist after you graduate, and what distinguishes you from other, other people from the business school, but other people from with the math major, and this is where it distinguishes you from the non-tech people. So if you're really interested in database, you should take the 9315 course, database implementation, where you use C to actually implement each of the relational algebra operator we talked about today. And for each of them, we have different implementation based on whether we have indexes or not. So, but in our course, we just need to know a little bit architecture about the DBMS so that we understand better how queries are processed and how to write efficient query and how to write safe queries. So today is more about efficient queries. So we need to understand relational algebra to understand how these queries are parsed by those engines. And in a couple of, maybe next week, we'll talk about how transactions are processed in DBMS engine and how transactions will make our DB application safe. So, so our view of the DBMS so far is we're treating it as a black box. So we write a SQL query, and then it sees our SQL query, and then it returns the result. And we don't know much about what's going on in here. And so we can think about the DBMS engine as a relational algebra virtual machine. So basically, it looks at, it parses our SQL query, translate that into relational algebra, and then it will find all kinds of equivalent relational algebra expressions and then compute the cost around it. So this is the layers in DBMS engine. So on top of it, we have query passing and optimization, and then query execution. And then the relational operators are central to this engine, and this is what you get to implement in the database implementation course. So, and in the lower layer, we have like files and buffer management. Basically, we need to handle how these data are stored on disk. And so we're not going to talk too much about buffer management in this course, and we'll talk about relational operators, and we'll also talk a bit about concurrency control in next week. So relational operators are basically the main character of today's lecture. So this is the workflow that I have repeatedly talked about today. So query gets in here, and then it gets parsed into a relational expression, and then the optimizer looks at your relational expression, which is a mathematical representation of your query, and then it breaks down into different relational operations. And it actually breaks down your expression into different sets of operations, and each of them is like step by step. And then the engine will estimate the cost associated with each plan, and then it will pick the one with the smallest cost approximately, and then it will execute that plan and return you the result. I mean, all of these plans, they lead to the same result, but the only difference is efficiency at this point. So that's the beauty about DBMS engine, is that it always guarantees the exact result, and the only concern in the database community has always been efficiency. And until recently, we have shifted towards other kinds of databases where we are relaxing that exact result constraint, and we're looking at more trade-off between efficiency and effectiveness. And we'll talk more about that towards the end of the course. So this is how the engine is parsing your SQL into relational algebra. And as you can see that the same SQL can be mapped to different relational algebra. And the different relational algebra, and for different relational algebra steps, they give you the same result in the end, but the processing time is going to be different. And the main processing time is determined by the intermediate result of each step. So that's why we need and that's why we needed to estimate the size of the intermediate result. So if you just want to, so let's look at these two imaginary tables. We have R and S. So R has A and B as columns, and S has C and D as columns. And then we want to do, so this is a equijoin, or you can also call it a theta join. So we want to join those two tables by matching B to C. And then we also want to filter on the condition that D equals 100. And then in the end, we want to project to column A, and then we want to rename that as X. So basically, I have just described four relational algebra steps to actually execute this query. So this is one way of mapping it. And another way of mapping, so this is the first plan. We join first, and then we select the tuples where D is 100, and then we project onto the A attribute, and in the end we renamed it to make the column name X. And this is another way of mapping it, and they should have the same exact result in the end. So another way of mapping it is that we filter the rows on the D column first. So because this condition is only imposed on the S table. So what you could do is that we could filter this first and then get that intermediate result to join with R based on the same joining condition. And the third and the fourth steps are the same, which are basically projecting into column A, and then we rename it to X. So as you can see that there are more than one way to map one SQL query into relational algebra expressions. And based on our experience in estimating the intermediate result size, what do you think is the kind of preferred way of mapping it into relational algebra? If you were the SQL engine, what would you do? Like, what is the, like, out of those two, what is the preferred way? Plan B? And why is that? Pardon? Okay. So specifically, which step are we processing less stuff? Mm-hmm. Okay. Okay. Yeah, that's exactly the reason. So the dominating cost of processing the query is basically by processing the intermediate results here. And if we can make the intermediate result as small as possible, and then the processing time is going to be much faster. So what we always do is that we always want to filter first and then join later. So even if you write your SQL query as like two views, you join first as one view, and then in your second view, you use your helper view, and then you filter, and then you project, and then you rename it. Even if you write it like that, SQL engine can still spot that and then change it around to make sure that it's executed efficiently. So the take-home story is that SQL engine is pretty fast. So it's pretty linear, it's pretty tolerate. Even if you write it, even if you intentionally write a SQL code that translates to this, it will figure out a way to swap things around, and so that the intermediate result stays small. So so that's what a SQL engine would do. And let's look at a couple of more examples. So so in this case, we want to find, I think we should look, I think this is the good place where we look at the code a little bit. Okay. So all of these demonstration files, they can be found in the, let me find which directory are there. All of these demonstration files can be found, I think I have in here. So you can, if you're curious, you can go to, you can copy all of these SQL files to your VXDB server, and then you can experiment with these examples. So let me do a quick demonstration of this relational algebra mapping to SQL, and towards the end, I will show you the SQL engine's view of these queries. So basically, we'll use something called explain to ask a SQL engine to give us the query execution plan, and really look at what the SQL engine is trying to do. So here, this is a selection. So let's look at what tables we have here. So first we need to load the schema, and we got some tables. Great. And then, if you're doing this at home, so you can. So before, if you're doing this at home, you need to create a database first, obviously, and before you load this table and data into there, and then you need to, and then it will populate the database for you, and then here we have a bunch of tables we can play with, and also some tables for testing the performance of SQL engine. So in here, so this is, we're just going to run each of them, and then be aware of the relational algebra corresponding to it. So here, this is the selection. We're doing a selection on the subjects. So the code, this part is mapped to a where clause, and for projection, if you want to project subjects into code and title, let's look at what subject table looks like. Subject table has ID and code and title, and let me look at subjects. So what if I want to do a projection into code and title? So do you think this is a good way to write it, or based on the schema? So there's a little issue with this approach here. So I'll give you a hint. So here, this is what the table looks like. We got ID. So this is the ID is the primary key. It says that ID is the primary key, and they have built a B-tree index on it. And then code and title are two attributes that we don't have any assumption on those attributes. It doesn't say they're unique. It doesn't say anything about those attributes. And what if we want to project this table into code and title? What should we just do? Select them, or what else? What should we do instead? So this works here, but what is the more robust way of doing this? So remember that projection maps to what SQL syntax in. So selection maps to where or as, but projection usually maps to select distinct, because in the projection, everything is the result is a set, so everything should be deduplicated. And in here, they happen to be deduplicated, but it is not guaranteed from the schema, because in the schema it doesn't say anything about either code or title being distinct. So the safe way to do it is we need to get the distinct code and title from them. And if we want to first select all of the rows corresponding to a condition, and then we project to some attributes, we can, this is what is mapped to. We can basically, the selection is mapped to your where clause again, and projection is mapped to a select statement. And of course, I would like to put distinct before that. And let's look at a couple of more examples of natural join and theta join, and after that we'll demonstrate how we can ask the SQL engine to come up with the query execution plan so that we can know what the SQL engine is trying to do. So this is an example of natural join. So we want to join students with people. So we want to do students with people. We want to first look at what attributes are there in students and what attributes are there in people. So in student, we got ID, and in, okay, I really should have put limit to 5. Okay, for students, we got ID and student type. Maybe it's local and international. And in people, we got ID and family and given. So if you want to do a natural join of these two tables, what will be the joining condition on? The joining condition will be automatically on the ID column, because that's the only common attribute of those two tables. So this is effectively an equi-join, because you have really specified SID equals PID. A natural join, you can basically say you can join students and tables on ID. So this is an example of natural join. It will match all of the, it will match the ID of student and the ID of people, and then it will grab the family name, given name, and the type of student it is. And for theta join is much more flexible here, and we want to get all of the subjects offered in 2025 term 1. And so theta join, we can put more complex joining conditions, and in this case, this is also effectively a equi-join. So so basically, we need to look at the subjects table. It has, okay, this is a terrible way of looking at it. So let's just look at the first few tuples, limit 5. So we can see this is the subjects table, and then we need to join it with the courses table. And if we don't specify what columns to join, a natural join will just grab the IDs and try to match those IDs. It will just try to match the subject ID with the course ID, which is a very terrible thing to do, because in a lot of databases, we have ID as the primary key for an entity. So for a student, you could have a student ID, and in the student table, it could just be called ID. And in the maybe staff table, they also have an ID. And if you just go ahead and join them, if you just go ahead and put impose natural join on these tables, what usually happens is that you're joining on very different IDs with the same name. So that's a terrible practice. So I personally don't really like natural join. I like to write all of the conditions explicitly. So I don't want them to just look at all these tables and then grab the attributes of the same name and try to match all of them. So if you just do natural join, it will match the course and the subject ID, and then it will be a mess. But alternatively, we should stick with what we have learned in the first half of the lecture, in the first half of the course, which is we need to look at the foreign keys of these tables and translate the foreign keys into the joining conditions. So the foreign keys tells us that, let me see what the foreign keys tells us. The foreign keys tells us that subject is a foreign key, the reference is subject's ID. So we need to translate that into the joining condition. So that's the correct way of joining these tables. We need to use a theta join. We shouldn't use a natural join. Okay? And I think for set operations is we could find out the student ID of the local students and the international students, and then we can perform union, intersection, and difference on them. And in SQL, difference is basically except. And one thing you want to be aware of whenever you're doing set operations is to make sure that the participating relations are union compatible, which means that they have the same schema. So in this case, if you're looking at all of the ID from the local students, if you just run that, it will the schema is just one column, and the international students should have the same schema, and that's why you can perform a union on them. And the same thing happens with, same thing happens with if you want to do an intersection with student ID and staff ID, then those two participating relations, they have the same schema and they're union compatible, which means that you can do intersection, union, and set difference. Okay, and I'm going to skip aggregation and grouping because it's not. We didn't spend a lot of time talking about aggregation and grouping in relational algebra. And note that in relational algebra, there is something called a gamma operator. So gamma operator translates to group by and aggregates. And if we ever ask you to write relational algebra that corresponds to like a group by and then aggregation, you can basically write group by, and then you can basically write the aggregations like max, min, and average in relational algebra expressions. So we didn't really talk too much about group by and aggregation in relational algebra. Okay, I think it's time for us to look at how explain works to help us visualize the query execution. So if we look at this query, what this query is doing is that it's trying to look at the subjects table, and it's trying to filter on code. So let's look at what this table, what do we know about this table? I think we have looked at this before. What we know about this table is that ID is the primary key, and then for code and title, we don't have like extra constraints on these attributes. So if you want to get all of the IDs, if you want to just select ID from I think it was subjects. Yeah, subjects, and versus if you just want to get all of the code from the subject, the SQL engine actually processes them differently because for ID, ID is a primary key. So primary key is the unique identifier of the table. So it is unique. And whenever we have a primary key, what happens is that they create a B tree underneath, so that whenever you want to do exact match or range query based on ID, it is super fast. So they basically have a multi-dimensional, a B tree is basically kind of like a multi-dimensional binary search tree. So in binary search tree, you have like one-dimensional numbers, you have a bunch of numbers, and then you build one binary tree for those numbers. And what happens with the B tree is that they look at all these fields, and then they organize these tuples based on the attribute you're trying to sort on. And in this case, primary key is ID, and that's why we can easily sort on ID. So let me look at what the so let me run a query again. So if you run this query, you got 4 courses. And how does SQL Engine actually look at this? So what it does is that if you put explain in front of it, it will actually give us the plan it adopted to return these queries. And as you can see that, what did it do? What did it do? It said it did a sequential scan on the subjects table, and then we need to filter on code matching this pattern. So that's what happened. Why do we need to scan all tuples in that table? It's because code is not a very special attribute. Code is just a text attribute, and we didn't build an index for it. It's not super fancy. And the only way we can know whether code matches something, we need to go through all of them and then check it ourselves. And what if we write a query that filters on, for instance, on ID? So let's just say that ID equals 1. So if you do that, do we really have any? Let me see what this returns. Okay, ID equals 1 gives us 3311 course. So if we ask SQL Engine to explain it, it will give us what query execution plan it adopted. So right now it also used sequential scan because probably because I provided a very small ID. Let me see, check something else. If we want to subjects. So if we want to find a range of the ID, so if the table gets very large, if you want to find a range of the ID, it will probably use the B-tree index to help us filter them. So let's move on to the other examples, and we can actually look at what explain returned to us. So here, let's run the original query first. So this is grabbing all of the names of these students. And let me see what the query engine actually did. What it did was it performed a sequential scan on the students, and then it used a hash table to map student ID to people's ID, and in the end, it aggregated the results and presented to us. So let me find a more interesting example where it involves an index. So let me see. This looks like a pretty complicated example. And so here we're looking at the courses and enrollments, and we're filtering the rows using code again. And we are also joining on these attributes. So this is a theta join, and followed by a group by, and then in the end we need to get these aggregates. So the result is just 4 rows. And what if we do explain analyze? What explain analyze does is that it will not only give you an execution plan, it will also give you the running time of that execution plan. So explain itself gives you the execution plan without running the query. Explain analyze gives you not only the plan, but also the real cost associated with it. Let me look at that. So, okay, this is kind of huge. Let me run again. So this is the this is the query plan, and then planning time and then execution. So in explain analyze, it not only gives you the query execution plan, but it also gives you the actual running time of that query. So in the future, especially in the exam or something like that, if you want to debug why your query runs very slow, then you can try to use explain analyze or explain to see the query execution plan returned by the query optimizer. So let's look at another example. Another example of the plan associated with the query without index compared to a plan related to a query with index. So let's look at the table first. So test performance, it has, let me just look at, select from test performance, let me just get 10 rows. So this is like a, you can consider this as an inventory table. So a store has some inventories and they have some items, and then they have ID, value, name, and category. And I think ID here should be the, ID here is the primary key, and that's the only thing we know about this table. And if we're running this, if you're running this query, we want to find out all of the rows where value equals 500. Let me see how many rows are there. There are many rows. And what is happening here? What's happening here is that because value doesn't have an index created for it, most likely, what do you expect from it? It will just go through every row in the table and it will perform a sequential scan. And after that, we can see if we create an index on it, it will actually make use of the index we created to boost performance. So right now, because value is just a plain, not so interesting attribute, if we want to filter on this attribute, we cannot really do better than performing a sequential scan. So I think this is a fairly large data set. If we actually if we're actually doing filtering based on primary key, it will likely make use of the B-tree index that we talked about. So right now, you can see that we get like 100,000 rows here. And what if I want to get everything where ID is larger than 100 and ID is less than 200? And that's these. And let's check again. Let's look at how explain give us the query execution plan. So right now, note that we are filtering based on the primary key attribute. And this is effectively a range query between 100 and 20. And supposedly, it should use the B-tree index for us because I've given it a rather small range. And it should know that if you go through all 10,000 tuples, it's very slow. And it should use the index scan instead. So as you can see, that is using the primary key index and is trying to answer this range query using the index. So if I change this, let me change the range here and see what. So if you change this to be very, if you change this to be larger than 1 and less than 10,000, it will kind of guess that that range query is basically the whole thing, and it will probably go back to sequential scan again. So if you change the range query to be between 1 and 10,000, 100,000, it will not do the sequential index scan for me. It will go back to the sequential scan. So as you can see that, this is super interesting. As you can see that, depending on the range query you give SQL engine, it will decide what is the best plan for your query. So if you say from 1 to 100,000, give me all of the tuples between 100 and 200, then this is a very small result size. In this case, if they make use of the B-tree index, they can quickly narrow down to this part, and then it will return this part to you. But if you're saying that, hey, give me everything between 1 and 100,000, then basically we're grabbing almost all tuples except 2 tuples, 1 and 100,000. And then the optimizer will take a look at this, and it will think it's not worth it. It is not worth it to use the index to speed it up. We might as well just do a sequential scan. So that's what's happening here. It is realizing that, it is estimating that, hey, we're looking at this many rows here, so let's not use the index and just use the sequential scan. So and let's look at the one more example of what if we create an index on the value of column, and then we look at what the query execution plan look like. So remember that before we were looking at filtering on value. So value is not an important attribute because we didn't create an index for it. So if we do that, it will do a sequential scan anyways. But now, if we create an index for it, so basically we create an index for this value, it will probably create an index that's not a B-tree index. It will probably create a hash index or something, but it will create some sort of index, some sort of a roadmap. And after we create an index for it, and if we run that again, very likely it will give us a different plan rather than sequentially scanning it. Okay, so it turns out that it created a different index, and now it is using a bitmap index scan on the index we just created so that we can get the result faster. You see? So, when you're at home, you can actually use explain analyze to get the running time, and you can compare the running time here. The running time here is 0.38. So if we drop the index, drop index, this thing, drop index, and then we run it again, and then it takes 6.32 milliseconds. So that's a huge difference. So basically, explain allows you to look at the query execution plan, and the explain analyze allows you to do not only give you execution plan, but also give you the runtime breakdown. Okay. So that's it for today, and next week we're going to talk more about transactions and query processing, query tuning, and in week 10 we'll probably do a revision and tell you like what do we expect from you in the exam. And all of these files can be found in let me see. All of these files can be found in that absolute path. I think we have in here. So basically, all of the demonstration files can be found here, and then you can try these at home. So you can try explain, analyze. Thank you.
Thank you.
Also Thursday works.
Yes.
Okay. Okay.
It's not Tuesday.
Okay. We'll correct it. Thank you so much.
Thank you.
How many percentage the theory and practical for the final exam?
Pardon?
How
How
many
many
percent?
percentage? Okay. Question. So if you look at the previous, I cannot show you that because
Okay.
so if you look at the past exams, the majority will be about the practical part. So we will also test your knowledge in theory part as well, and intertwined with the practical part. Yeah, like we
So
could
is-
ask you, hey, this is a bad query, identify the problem with it, I think using something like that, and then eventually you write a lot of SQL code, definitely.
So like it's 60% practical, which is say that, or like we cannot guarantee.
We'll talk about that in week 10.
In
We have to